All right, when we see this integral notation applied to some expression like we have here, that means we need to take the antiderivative of that expression. One thing I might make sure of before I get started on this problem is I might make sure that I have each individual term written so that I can conveniently apply basically our power rule to this expression. So the x cubed is good, the plus 4x is good, but I'm going to rewrite this 1 over x to the fourth as x to the negative fourth, and the plus 7 as a constant. That's fine as well. So this is our expression that we're going to take the antiderivative of. As we take the antiderivative, our notation drops out. We simply go through term by term, applying our power rule. For the x cubed, we're going to add 1 to our power, get x to the fourth. Reciprocal is 1/4. Place that in front. For the 4x term, we're going to add 1 to the power. We're going to get x to the second. Reciprocal of 2 would be 1/2. That 1/2 gets multiplied to the 4 in front, leaving us with 2. We're subtracting. We're going to add 1 to the power here of negative 4. So that's going to become negative 3. Reciprocal of negative 3 is negative 1/3. So the negative 1/3 goes to the front, meaning this becomes a positive now, 1/3. And then we're going to tack on our constant value of 7. If we tack on that constant value of 7, we attach an x. We've made our way through all the terms, so the only thing left to do at this point is make sure we've added on c to represent any constant, and we've got our antiderivative. So considering the antiderivative for this problem, what I might do first is I might try to do some algebra to simplify this problem out and see if I can't break this up into some individual terms to work with. One thing I might do is I might bring this root up to the top, change it over to a negative power, so that would be x to the negative 1/2. At the same time I'm bringing that up, I notice that this x plus 2 quantity squared is something I can expand out. I could FOIL out basically x plus 2 times x plus 2. That would give me x squared plus 4x plus 4. Now as I look at taking the antiderivative, I'm pretty close to something I can work with, but I do have a product, which we cannot have. So I need to distribute, and as I distribute, I'm going to add my exponent powers together. So x to the negative 1/2 times x squared, if I add those powers, that'd be x to the 3/2. Plus, got 4, this is x to the first. So if I take 1 and add on negative 1/2, I'm going to get x to the 1/2. Then plus 4x to the negative 1/2 for that last term. So I'm taking the antiderivative of this expression, which I've now spelled out into 3 individual terms. If I go through and apply my so-called power rule to each term, I'd add 1 to the power here on x to the 3/2. Adding 1 would give me 5/2. Reciprocal is 2/5, which goes to the front. Plus, I've got x to the 1/2. If I add 1, that'd be 3/2. Reciprocal would be 2/3. The 2/3 gets multiplied to the 4 in front, giving me 8/3. Plus, here I've got x to the negative 1/2. If I add 1, power is going to be 1/2. Reciprocal of 1/2 is 2. That gets multiplied to the 4 in front, leaving me with 8. I've taken the antiderivative with respect to each term. Only thing left to do is account for the constant. So add on c. There's your antiderivative. Now as I consider the antiderivative of this problem, considering what I've done on the 2 previous problems, I've tried to find a way algebraically to spell everything out so that I've got individual terms to work with, making it easier to take the antiderivative. Here it's not out of the realm of possibilities to go ahead and expand this out and do the same thing, but accounting for this power of 5 and multiplying this out 5 times is not going to be much fun. So this is where we introduce some substitution as a technique. We let u equal the 1 minus 2x, because that is the part that is trapped by the parentheses here. And as I introduce this variable of u, I rewrite a new and improved problem over here, where the u is taking the place of the 1 minus 2x. That was trapped by a power of 5, so I write u to the 5th over here. Now, as far as everything else is concerned, because I've now taken care of this part, I still need to do something to adjust for this dx, since that's in terms of x, and I'm trying to set up a new problem in terms of u. This is where I take the derivative of my equation down here for u. Derivative of u would be 1 du. Derivative of 1 would be 0. Negative 2x would be negative 2. And then I'd write a dx because I took the derivative of x. If I'm trying to replace dx, I get dx down here by itself by dividing the negative 2 over. That would give me negative 1/2 du equals dx. If I'm trying to replace dx, I can replace that with negative 1/2 du up here. So the negative 1/2 goes in front, du at the end. I cross this off my original problem. I've crossed everything out of the original problem, so I know that I'm ready to go with my new and improved problem over here. As I take the antiderivative of the new and improved problem, I have one term to account for, one term where the power is 5. So I add on 1, I get u to the 6th. Reciprocal of 6 would be 1/6. I need to multiply 1/6 to the front here with that negative 1/2. That gives me negative 1/12. I've taken the antiderivative of my single term. I have to account for the constants, so I add on c. At this point, the only thing left to do is replace that u with what we let it equal in the first place, so that we get everything back with respect to the original variable that was x. So u is going to be 1 minus 2x. It's all to the 6th now. Tack on your c. There is your antiderivative. On this problem, I'm taking the antiderivative of a quotient. So we've grown accustomed to doing this anytime we're presented with these fractional expressions. We tend to try to write everything so it's on the same line. So I'm going to take this expression on the bottom. I'm going to bump that up to the top by using what I know about negative exponents. I'm also going to convert the root over. So I'm going to have x from the top multiplied to a quantity of 16 minus x. All of that raised to a power of negative 1/3. So I'm trying to take the antiderivative of this expression. What stands out is I have a product, which we can't have. And I also have a scenario where I can't easily distribute that x through, so I have to use the u substitution. I'm going to let u equal this piece that's inside the parentheses, 16 minus x. As I introduce the new variable in, I set up what is eventually going to be my new and improved problem. If u is 16 minus x, and that 16 minus x is trapped by this power of negative 1/3, down here in the new problem, I write u to the negative 1/3. So that accounts for this part. We still need to figure out a way to account for these two parts. So what we do, we take the derivative over here of my equation. Derivative of u is du. Derivative of 16 is going to be 0. Negative x here is negative 1 dx. If I look at what I'm trying to replace, an x and a dx, I can at least replace the dx if I solve for dx over here. Solving for dx over here, divide the negative over, and dx equals negative du. So I take the dx out, I replace that with a negative du. So I'm going to place the negative in front of this u to the negative 1/3. As far as what to do with this x, though, anytime we've got that extra variable that hasn't been accounted for yet, this is where we go back to what we let u equal, and we solve for that variable we need to replace. So I solve for x. If I solve for x, I'm going to get 16 minus u. So I can now squeeze in here, if I make a little more space. Squeeze in here a 16 minus u as a quantity, which is getting multiplied to this other expression, negative u to the negative 1/3. That now takes that guy out. So we've accounted for everything. We now have a new and improved problem down here where we still have multiplication involved, but with this multiplication it'll be a little easier to deal with because we can distribute this negative u to the negative 1/3 through. We distribute that through. Still haven't taken the antiderivative, so the integral notation still needs to be in there. I've got the negative u to the negative 1/3 times 16. That's negative 16 u to the negative 1/3. I've got the negative u to the negative 1/3 times negative u. That becomes positive u. Add your exponents, so power 1 here and negative 1/3 go together to give me 2/3. And then we've got our du at the end because, again, we haven't taken the antiderivative yet. We're still in the simplifying stages. We have individual terms to play with at this point, which means I can take my antiderivative. So I lose my integral notation as I take the antiderivative. I look at the power on this first term, which is negative 1/3. I know my rule is to add 1, so I add 1 to get 2/3. I take that reciprocal of 2/3 and I multiply that to the negative 16 in front. If I multiply that to the negative 16 in front, well, it'll be negative 16 times 3/2. That'd be negative 48 over 2, or negative 24. For my next term here, as I take the antiderivative, adding on, we're going to add 1 to the power of 2/3. That would give us 5/3. Reciprocal is 3/5, so that goes to the front. We've taken the antiderivative of each individual term. Only thing left to do is tack on the constant. So at this point, your final step would be go back, replace your u's with what we let u equal in the first place. That gets everything back in terms of the original variable x, and you've got your answer. So last antiderivative example here, we've got a trig function. Our argument on the trig function is a pi x combination. So when we're dealing with trig functions and trying to take an antiderivative, if we're going to incorporate this u substitution, we've got the single trig function. We should let u equal whatever the argument of that function is. So in other words, whatever follows that function. Let u equal pi times x. So the pi times x is plugged into the cosine function. Since I'm introducing the new variable of u, let me set up a new and improved problem. Over here we'll have the cosine of u. That takes care of this part. Meaning the only thing we still have to replace is a dx. So I come down here to my u equation. I take the derivative. Got du equals. Pi is just a number. X is dropping out, so it's pi. And then don't forget the dx because we took the derivative of x. If I want to replace dx up here, I solve for dx down here. I divide pi over. So pi is just a number. If I divide 2 over, it'd be 1/2 du. Divide 3 over, it'd be 1/3 du. Here, it's going to be 1 over pi du. So now I can take this dx out. If I put in the new and improved problem, a 1 over pi and a du. If we look at what we have now, we can take the antiderivative of this expression because we got some rules we can apply that have to do with trig functions. We know cosine and sine go hand in hand whether we're taking antiderivatives or derivatives. So I'm going to have a 1 over pi down here. The question becomes, is it going to be a sine of u or is it going to be the negative version? Well, how I check? I take the derivative of this part. The derivative of sine of u would be positive cosine of u, which I have up here. Therefore, I don't need a negative down here with my antiderivative. But that's how I check. Take the derivative of this part, go back up to this expression. So now I know this is correct. I've taken the antiderivative of the trig expression. I account for the constant. And then I go back and replace u so that everything's in terms of the original variable x. I've got the sine of u, which is pi x, plus my constant. There's your antiderivative. Here we got an example of a problem where we're given a function and we want to find the approximate area beneath the function's curve above the x-axis and on the interval from x equals -2 to x equals 1. In approximating this area, we're going to use rectangles. In fact, we're going to use 5 of them. And no matter what approach we use, whether it's right-hand sum or left-hand sum approaches, we're going to start by finding the base. And the way we find the base for all of our rectangles is we take where the interval ends, we subtract where the interval begins. So it would be 1 minus -2, and we divide by the number of rectangles. So divide by 5. Our base here is going to be 3/5, or if we want to use a decimal approximation, to actually be exact here, 0.6, we could do that. To set up a right-hand sum, what we do is we let our area equal our base of 3/5, or 0.6, times the sum of 5 function values, since we're dealing with 5 rectangles. So I've got my 5 function values set up. Since it's a right-hand sum, we start at the right edge of this interval. So the right edge of the interval would be at 1. And then we subtract our base lengths backwards so we can get our respective values here to plug in. So if 3/5 is my base length, or 0.6, I'm going to take 1, I'm going to subtract 0.6, and I'm going to get 0.4, or 2/5. At 0.4, I'm going to subtract 0.6, get my value to plug into the next function. That's going to be -0.2, or -1/5. I'm at -0.2, I subtract my 0.6, I get -0.8. If I subtract if I subtract 0.6 again, now from -0.8, I get -1.4. So here are my values that I'm going to plug into my functions. And to get those values pretty quickly, so that I can add them all up and then remember to multiply by base of 3/5, I can go to my graphing calculator. I can plug in my function. Once I've plugged in my function, I can use my table setup here, second window. And I can adjust the independent variable to ask. Now go to my table, which would be second graph. And in my table, I can take these values, 1, 0.4, -0.2, and so on, plug that in to figure out what the function values are going to be. So if I take all of these values right here, I add those up, since that represents all of this part here, multiply by 3/5, that will give me my approximation for my area using a right-hand sum approach. It looks like on this one, the approximate area, rounding off to say, 3 decimal places, would be 6.564. So now if we want to look at how to do a left-hand sum approach, in a very similar fashion, to find our area, we're going to take our base of 3/5. We're going to multiply to the sum of 5 function values, since there's 5 rectangles. And since we're using a left-hand sum approach, we're going to start at the left-hand side of our interval. That'd be at -2. We're going to plug in -2 to start, and then we're going to add our base lengths on of 3/5, or 0.6. So if I add on 0.6 to negative 2, I get negative 1.4. I plug that into the next spot. Add on 0.6, get negative 0.8. Add on 0.6, get negative 0.2. Add on 0.6 one more time, get 0.4. So now I take all of these values and plug in. Since I've already set this up for the right-hand sum, it's not going to take me too long to figure this out because I've got most of my values already. Really, the only new value I need to calculate is negative 2. So I enter that in. I find out that's 4. And now I add up all of my values basically from 0.4 here down to negative 2. I add up these results on this side. Once I get that sum, I multiply to 3/5. That's going to give me my approximate area. So assuming I've done my calculating correctly, rounding off to 3 decimal places, I've got 7.914 as my approximate area using a left-hand sum approach.